My name is János, and today I will talk about how we created an adaptive platform at Internet News. Who am I? I have a long relationship with software engineering. I started when I was 11 on a Commodore Plus/4, and after the Commodore Basic, I moved to assembly, and I kept as close as possible to the hardware for a long time, and then I moved to the web services when I was at uni, and since then I'm still at the web world. I started a consultancy firm 10 years back, and after 10 years I moved to a consultancy firm called ZeroMQ, and it's one of the largest consultancy firms on the world. I worked on projects like Royal Mail, Post Office, Parcelforce.com, Bristol City Council as a software engineer lead. And 5 months ago, I joined to a startup called Internet News, which is a platform for employers to find fresh talents for their businesses in an automated fashion. We try to capture as many data as possible about the candidates, and we use a matching algorithm, or actually not one but many, to match internships against the candidates. So we try to minimize the time for the recruitment. And to do this, every startup normally starts with an MVP, or starts with a great business idea, and then they move or they exploit their business ideas, and they reach a point when they need to scale. And this is when I arrived to the project, and from a monolithic architecture we moved to something service-oriented, or actually microservice-oriented architecture. Okay, so I mentioned, and the title of this talk is how to create an adaptive architecture with ZeroMQ. And for first, we should clarify what is an adaptive architecture. And according to the Wikipedia, adaptive architecture is a system which changes its structure, behavior, resource according to the demand. That means normally non-functional requirements has to, or actually the system has to adapt to the new functional requirements, or if the parameters of the external environment changes, then the system should adapt to satisfy those requirements. And as I said, almost every software starts in small as a monolithic platform or architecture. And some examples, I guess you recognize where this photo was taken. It's the Stonehenge, and one of the key thing with Stonehenge is it seems like a successful project, but no one knows anymore what was the original purpose. It's an old project. We can consider it successful because nobody really complained in the last 1,000 years about its functionality. But the original engineers left the project. There's no documentation. There's no tests to understand how the internals of the system work really. And therefore, if somebody would like to update or upgrade or add some extra functionality to such a system, the new developers would be scared because they don't know where to break these systems. So this is a kind of attributes of a legacy system. Oops. So, I really like this photo. I don't know how much do you see, but I recognize almost every role as you can utilize in a software projects, like always doer, project manager who is always happy in the background, someone who tries to analyze the state of the system, some senior people who WTFing, and a scared developer who realized what he's facing. Another example is it's a quite tragic example, but it also occurs a lot with big systems. This is the biggest battle cruiser what Britain ever made. Its name is HMS Hood, and when she was laid, and sailors has a bit of dirty mouth, but when she was laid, she immediately became the flagship of the Atlantic Fleet, and sunk by a single hit in the Second World War. So it was quite. Fortunately, you can't see it, but one of the part of the ship had just one single hit, and she was sunk in 3 minutes. And it's the same with big applications. They are too complex to do functional tests in every aspect to realize its flaws and risks. Another one. This is a code graph of a popular open source project written in Java. And the code graph shows us the dependencies between objects, which are marked with the white dots, and the classes, which have the other shapes. Some of them are abstract class, some of them are final, and some of them are classic. But the point is, can we determine or describe the behavior of, for example, this instance? Probably we can't, and it's really hard to write behavior-driven test or behavior test for such software. Okay. Another, maybe a good example for monolithic architecture is the Linux kernel. These numbers demonstrate the changes in the recent 120 days in the life of the Linux kernel. It shows how many developers worked on it, when it was released, how many lines were added, and how much was removed. And these are massive numbers. And even if 2,500 developers contributed to the Linux kernel, only 400 made a significant change on it. That means on the planet, there's only 400 people, probably maybe 500, who can actually understand the whole architecture of such massive project. And it's fine for an open source project because you can enjoy the attention of the developers of the world. But if you work for a client or you develop a platform and you do something very complex, it inherits a huge business risk. So, as a summary, what's wrong with the monolithic architecture? Monolithic architecture intimidates developers. It's hard to do changes in these softwares. It's often they have a complex build script, and it's pretty tough to deploy them. So if you have a massive software, which probably is some hundreds of megabytes or gigabytes, it's pretty hard to do continuous integration on such on such a system. It also, and this is the this is the toughest part. It requires a long-term commitment from technology. If you pick a programming language, you have to maintain it over the life of the whole project. If you pick a database, it's really tough to move from one database to another because all the components has to reflect to the new one. And because of that, you can't really do sufficient or enough functional testing. And if you do functional testing, because a system is very slow moving, it's really hard to, or maybe you can't solve it because there's no enough time to run all the tests between the releases. So if you have to, for example, model a user journey with payments and all the gateways, and this is a website, then it probably takes a couple of minutes just to create a user, tear down the user, and go through the journey, play all the scenarios. So if you want to do a couple of releases a day, as Netflix or Facebook does, you can't do this with this kind of architecture style. And because these applications are massive, if you develop in Scala or Java, if you occasionally some services need a minute or half a minute to restart, and it's really tough to orchestrate services or do load balancing, because if you have hundreds of servers, you just to go through all the restarts after the successful deployment, this just takes too much time. And for developers, it's also a big problem. It overloads the IDE. If you import the whole project because you want to see all the classes and instances, when you type in the integrated development environment, it offers you auto-completion, and if you have tens of thousands of classes, then it's just makes the whole system slow. Also scales inefficiently. So if you want to deploy and scale horizontally these applications, you have to deploy all these massive chunks onto each server. And some parts probably are more heavy, some of them are more lightweight. So you shouldn't really copy all of them in the same ratio onto the same server. Some of them maybe it would be enough 5 instances. Some of them has to be deployed to all the servers to have efficient load balancing. Okay, this is a quote from one of the core members of the ZeroMQ team, and he says that the future of code we are taught to code. The future code is distributed code. The future code is chatty code. This means there's a tendency to move toward applications or services which heavily talk to each other. If you imagine, for example, if you want to log everything which happens in your system, that's a massive volume of messaging. If you want to also do some or add some flexibility in the system to alter some messages to something else, it's maybe doubles or triples this volume. And then we reach to the microservice. It's actually what is a microservice? It was a kind of movement to distinguish the current state of service-oriented architecture and the lean version of this. Service-oriented architecture started from the paradigm to break down the application into individual parts, individual deploymentable parts, or segregation on the operating system level. So classically, this means you have different runtimes running in the system, and these runtimes communicate with each other. So according to Martin Fowler, services are out-of-process components of the system. And microservice try to do this in a right way. Because in the recent years, if you bought a book about service-oriented architecture, it was more about business governance, kind of not necessarily technically related stuff. And the whole point is to support not just the business needs, but also the technical evolution. And the people who initially worked on or named their products microservice, they try to distinguish their big, heavy services from their product. Are you guys anyway agree with this? Okay, so if you use or if you try to ever integrate with big, massive systems like Microsoft Dynamics with Adobe Lifecycle, these are services, but these are applications or platforms on its own. So they are integrating these are not necessarily service-oriented architecture, or word by word it is, but it's not fulfill the original idea. Okay, so why would we use microservices? This attribute or this explanation comes from the SOA. You can deploy it independently. That means you don't have to buy the same size of servers for every kind of service. So some of them are more heavy, may require more memory. Some of them are more lightweight. And you can deploy them independently. If you have a version upgrade of one moving part, you don't have to upgrade all the parts. And it's Uncle Bob Martin's favorite attribute of microservices. Independent scalability, independent context. This is if you do domain-driven design, then you met with the idea of bounded context. That means the same application can be approached from different directions, and you can segregate your application according to this. And that means you might implement something in a very different way from one perspective than from another. And maybe these use cases are also different. So different people, different systems could use the service. And you can do this with a service-oriented architecture. And my favorite one is simplicity. So if you develop something which has 10 million lines of code, it's really hard to get into. Maybe it takes weeks or months to understand the system, and after a year you will still don't know all the moving parts of the system, because if you work with 20 colleagues who work on the same code, it just changes too much, and you can't really pick up the changes. And if you break down to, for example, 2,000 or 3,000 lines of code services, those can be delegated to maybe less senior people or new joiners, because it's easy to look through. It has a very strict scope. Maybe if the architect was a good one, the contracts between other services are well defined. So it's easy to test, easy to understand these. And faster build time. If you do continuous integration, it's a key thing. If you compile a massive Scala application, it might take an hour or two just to compile it. It's simply unachievable to do real continuous integration when somebody commits a new change and a build script triggered, and it's provisioned to everyone. It's just simply can't happen with too big application. And faster startup time. This is important if you work for high availability, and it's quite obvious if you do 3 or 4 releases a day. Cache invalidation, the parts which are involved in caching are occasionally restarted after every deployment. And sorry, and it's just you can't do this with big applications. So the good parts: shorter development time because it's easy to look through the individual parts. Higher accuracy. So if you work in an agile project and or in a startup where you have very limited budget, then it's really key to get or exploit or get feedback from your idea. So this because it's simpler, you can deploy it faster, you can scale better, you can get feedback earlier from the users, and this means higher business accuracy because you can change faster. Better availability because you can scale the parts against better strategies. Low latency. This can be a contradict because we could expect, okay, if we use services, then the network is involved, or the speed of the network is involved in the communication. But if you break down into concurrent parts the application, you can trigger individual processes differently, and in an asynchronous way, at a point you can synchronize all these events, and maybe you will, or not maybe, in most of the cases, you end up in a faster application. Any questions? No? Okay. Reusability. This means if it's actually the same principle of using shared libraries. If you, for example, pick one service like sending a mail sender service, which I don't know has plugins for Mandrill, Sandwheel, or whatever service do you use. It's easy to use this service for other applications. And if you have hundreds of microservices, it's probably, or the chance to reuse these parts are way higher than if you would have a monolithic application. But there are some tricks with microservices. You have to change the way you're thinking, because you can't really solve the new problems with the same thinking as you created it. You have to design good contracts. You can't really, okay, on the fly, I will send some messages. we will update the API as we evolve. This most of the time results bad or slowed down development because, as I said, there's high chance to reuse the component. Then if you change something, maybe other components are involved. So it makes a tightly coupled system. So you have to design your contracts well, or you have to do it better than as you would probably normally do. Also, you can't let the integration to the end, because these systems are the whole point of having this system to end up with simply a faster and more maintainable system. That means you would probably design your contracts against another service. So if you don't really know what you will integrate your service, then you don't do it any better than the old style. Your team have to support it. This is usually the trickier part because it requires some kind of paradigm shift within the team. And if you heard about Conway's law, that means your architecture probably, or there's a almost 100% chance to reflect to the organizational change. So to create a snappy, fast, easy to maintain, agile application, your team has to be agile and flexible and snappy as well. And here are the ugly parts, which are the drawbacks of having microservices. Because you have hundreds of services, or let's say just 10, but you have 50 servers, then that means you will end up with a massive system of 1,000 services, and you have to orchestrate this. And you can't do this without proper tooling. I mean, like monitoring, logging, and auto restarting tools. and also continuous integration is also key, because you can't really test the system at this scale without that. And easy to overdo. If you check the SOA anti-patterns or microservice anti-patterns, most of them are coming from to overdoing things. So, for example, microservices is about to break down your system according to boundaries, context boundaries, to smaller parts. But you can overdo it. You can say, okay, back to the emailing example. If you have plugins, you might say, okay, then I will have a SendGrid, Mandrill, or Amazon SES service, and you can do it endlessly. Then I will have a TCP, DNS service, and a UTP one, and it's just too much. And one other anti-pattern is more about behavior, because microservices allow you to combine other technologies. So maybe some task is the most efficient to integrate in Java, but maybe other problems have a Lua script or whatever, or Python library. So why wouldn't you use that if your developers are agree with that? Then you can end up with using very unstable technologies, or you can generate a siloed team where you use all the languages of the world, but only one developer knows, for example, Ruby, another one Python, another one C, and you will end up with a very fragile team and structure. And also, you have to design partitioning strategies. So the key problem is not necessarily the context, but who owns the data. So if you denormalize your database, or if you have to implement around the context the same entity, then you have to be very, very careful. For example, a customer entity or aggregate, which service will own it? The sales service, for example, or the e-commerce service? So it's a tough problem. Usually, you would end up implementing the same entity in both systems, because you want to avoid the dependency on each other. So these partitioning strategies can be based on functionality, bounded context, data model, and the most popular one is the bounded context. And using data model one is quite rare, because it's hardly unlikely to have a system which just retrieves data or doing create, read, update, and delete operations only. You want to transform this data, you want to process this data, and the last cases only works for when you just retrieve and maybe insert or update this data. And there are some challenges. You have to solve the eventual consistency problem. So if you have many services, there are always they are not in sync. So maybe not all the service or all the database or all the data stores have the same state in every time. So you have to think about what will happen if, for example, there's a split in your network and or between your data centers. And as I said, it's also a problem how to segregate this data, how to deal with slow transactions. So you don't want to starve one of your components in the system just because something happens. So you have to fail fast. And also an issue with task delegation. I noticed a problem when if there's a massive system, somebody might pick a task one time. And if there's a new feature request or bug report, he will probably pick that bug report which belongs to that function. It's fine until a point when people feel, okay, this is my service, and if there's a criticism against it because it's too slow or something is not good with that, then he feels as a personal assault. So you as a team leader should consider to rotate the team according between these components. And so now we know what microservices is, and we probably created in the system a couple of them. But if you have eventual consistency, if you have, or you can't trust in the network you deployed this application because there's no such SLA in your contract, then you have to be crafty. And one solution could be if you use sessions in your load balancer. So if you, let's say, if you have, for example, one request, and you have, for example, 50 nodes in your system, then you want to route the new request from the same client to the same nodes. It's probably not efficient load balancing, but you can avoid inconsistencies. Another one is people often likes the state machines, but if you have just eventual consistency, you can't have state machines because your system as a global don't have the same state in every node. Or if you have the replica of 5 of the same service, they might not in sync. So you can't rely on that. You would get the same data back. So if it's the same classic problem with the master-slave replication in SQL databases. So if you want to say that, okay, the write operation will always go to the master and the read maybe from the master, from the slave, if there's a split between the two, you probably break your application. And one solution could be event sourcing. So you don't persist the state of your entities, but the events which transform these entities. So that means you can replay these over time. It's the same concept what SQL or traditional database is using when they do replication. So you persist or store the events until a given point, and then you can replay it. And the benefit of this, you can reroute these events. So if there's an event like the user updated the profile, you probably use a publisher subscriber architecture, and this event goes from the publisher to the subscribers, and this is what you need to persist, not the state, what data was actually stored in the database. But you can also overdo this. If you don't take snapshots, you might end up with just a massive log, and if your nodes are out of sync, then it will just take a long time to replay all these events. Does this make sense? Okay. So we are getting there, how we use ZeroMQ. And now we have services. Now we do know how to deal with events and changes in the system, but we need to somehow let these components communicate with each other. And the classic answer to this is to use an integration framework like Apache Camel, for example, to tie together these services, or using a more robust solution, the enterprise service buses. Both of them are bit over the top for this because we expand the very, very low latency. So for example, Mule published not white paper, but a kind of advertisement of their solution, and they are brilliant. So I do love Mule. It's not really against them. So if you check these numbers, they have 8,000 transactions per second, 2-second response time on system level, but just 6 millisecond latency. These are awesome numbers. So these are quite good for a 20 kilobyte SOAP message. But you need a 24 CPU and 36 gigabytes of RAM for this test. So the test case is published or can be found on the website. But it's fine in many cases. But if you have hundreds of such service and literally millions or billions events in your system, this is not good enough. It's perfect for the classic integration cases, but not necessary, or it's just too heavy for us. So if you have loads of events, I mean extreme rates, so if you have thousands of services, I mean in the whole system, then and if you do logging or you have many publishers, many subscribers, that's extreme rate of events. How would you do fault tolerance? So if you have an ESB, you have to care about replication and all sort of things. So it adds an extra layer of complexity to you. One solution could be NSQ. It's a message queue like ActiveMQ, but it's more lean. If you check just the last line, there it can push or its throughput is for 2 million operations per second, 40.8 microsecond, not milliseconds. So it's 3 orders of magnitude faster than a Mule solution. Of course, it's not that robust. It's by default it's a non-durable in-memory message queue, but in 99% of the cases, it's still fine. You can do clustering, and it's quite seamless. It's written in Go. Have you heard about Go? Google Go? It's a relatively new programming language which tries to aim the garbage collection and concurrency by default. And one of its benefits is you will, when you compile your application, you will end up with one binary without any kind of dependency. So there's no dependency on any other library, easy to deploy. And NSQ is written in that language. It's pretty fast. If you are unlucky, then you probably end up 2 or 3 times slower application as you would written it in C++. So it's pretty fast. It supports encryption. You can do streaming, which is not common in the message queues, and no broker. So the whole architecture of NSQ is having it's actually consists of 2 applications: a lookup daemon and NSQ agents. And the lookup daemon is what you set in your services. So they will query, okay, I would like to send this message. It will, your application don't see it, but it will query an agent, a list of agents, and then it will connect to the agent. So it's quite seamless. If you start an NSQ agent, all you need is just to specify the or in the simplest case, a lookup daemon address, and that's all, and it's joined to the cluster. Okay, so what's the problem with this? if you do your programming in Google Go or Erlang, which both languages are support concurrency by default, you probably can stop here because most of what ZeroMQ will offer is happy with concurrency. But many languages like Java or C or Python or PHP, these languages does not support concurrency by default, and concurrency is just stuff. And these solutions are still slow. So we classically think about how do we integrate e-commerce systems or financial transactions. What if you are an architect in a game developer company? Milliseconds or seconds are just no-go in such applications. And you can also do microservice-oriented or microservice-based architecture style in such projects. And also, if you have to deal with concurrency because your language doesn't support using multi-thread like in Java, or in C, it's just pretty tough. There are loads of anti-patterns or ways to fail it, and these are just some of them. And block convoys or block-free reordering. If you want to reorder, for example, a number without blocking or an associated array, it's pretty tough to make it thread safe. And yeah, pretty much it. But there's a solution, and the solution is what I found is ZeroMQ. And it's actually how they advertise it come for the networking and leave for the concurrency. And that means it's basically it's a library. It does not have a standalone server, so its name is quite misleading. It's not a message queue. It's a communication and concurrency framework, and it acts like a tiny server in your application, and it deals with network sockets, or we will see a little later. But it's one of its key attributes is asynchronous seamlessly. So when you, for example, bind to a port and you have a client which connects to it, the clients will only connect to it when it transmits. And if the transmission fails, it will seamlessly retry it without any extra coding. And it has more than 30 language binding. And some of them are not binding, but because ZeroMQ is quite small, it's easy to rewrite in any other languages. So for example, the Java solution is written in native Java, and it's way faster than, for example, than a classic C binding. And ZeroMQ has two kind of components, main components. One is a context, and another one will be a socket. The socket will be very different what you would expect if you programmed in Unix systems. So these are not domain sockets. They behave the same. The authors of ZeroMQ, they try to implement or create an API which very, very close in terminology to C, but or sorry, to the POSIX networks, but it's not the same. So one is a context. Context is it acts like a container for the socket. So later we will see a code example. When you create a context, you usually have one context per process, and you put all your sockets into it. Contexts are tested, so you can share it across your application. So if you have, I don't know, 50 port bindings, all your threads can use it without any caveats, because ZeroMQ does it for you. And this is one of its biggest advantage. You can do concurrent programming without the drawbacks on the previous slide. Are you familiar with concurrent programming? Okay, so please confirm it's not an easy thing. Or you are lucky, or way smarter than me. Okay, so all right. So ZeroMQ sockets. As I said, these are not Unix domain sockets, and I try to market with a bold font. What's the difference between, for example, a classic message queue? So there are very, very fast message queues. But why ZeroMQ is awesome? Because it supports in-process communication and inter-process communications as well. So it's not just network sockets. You can do it, or you can organize your application in a very different way. So, for example, if you want to communicate on the same host, all you need is just to change the endpoint name. So we will see later in the examples. And using inter-process communication or in-process ones, those are way, way faster than using the domain sockets or TCP sockets. But you can also use PGM and ePGM. These are datagram protocols. So, for example, you might want to just publish events in your system to your logger service. And okay, within a system, it's probably fine to use UDP packets, because we can expect that the system is reliable. And if the message lost, then who cares really? So it's not a big disadvantage to lost every 1 billion, every billion, I don't know, user logged in message. Maybe it's critical for some cases, but there are 99% of the scenarios are not really that mission critical. And you can do also multicasting with ePGM. And as I said, because ZeroMQ is more like a concurrency framework, you can use the same socket multiple times, so you don't have to really care about who or which thread is actually using those sockets. Sockets are not thread safe, so if you want to expose these sockets, you have to expose the whole context to other threads. But these are not tough. So these are not. So it doesn't add too much complexity to your application. And all the network connections happens in the background. So as I said, when you connect your service or when you transmit it, you don't really know whether it was sent or when it was sent. So these are asynchronous communication. That's why your application will be way faster. And the only drawback is you don't have direct access to these connections. So if you, in some cases, for example, NSQ does not use ZeroMQ. And why? Because they wanted to tweak these TCP sockets. So this is what you can't do with ZeroMQ. So if you want to tweak the TCP headers or the IP headers in your communication, this won't happen with ZeroMQ. And here's a tiny example. It's written in PHP, and this example contains a client, both a client and a server. And it's very interesting because you would expect you can actually run this example if you copy and paste to a PHP interpreter. Here you will you can run it. And you would expect this is a sequential code, but the binding happens in the background, the connection happens in the background, and the real connection will be built up when you send a message. And it's literally just lines of code. And here you can define the endpoint, and or endpoints actually. And why this is great, because if you use external configurations, we will see it later in an example, you don't have to change your application when you change the endpoints. So if you, for example, have, or as I said, we moved from a monolithic application to a service-oriented one. And we could do this without really changing the application. So when a new component was ready, then all we needed just to reconfigure the endpoint, and the system reflected to it. So in between, we used an inter-process communication, but when we organize that to another service, then it will ended up in a TCP communication. Or if you are sure your nodes are on the same server, then you can use IPC, and you don't have to change the code. And this is why we picked ZeroMQ. And you would expect the C version of this, because as I said, there are more than 30 language bindings, and the original ZeroMQ is written in C, and most of the examples in books are written in C. Unfortunately, I can't scroll it, but please believe me, it's not more than 30 lines of code to do the same in C. All the so the functions are quite similar. All the differences are mostly the attributes of the C when you want to do a memory copy, or you have to do explicit allocation of the variables. This is how you do this. Sorry, any questions with for the examples? These are very, very basic examples.
If you have to specify all the endpoints that you want to communicate with,
yep.
How do you go about implementing something like complete consumer?
There will be another example, or at the end of this talk, I will talk about how can you do service location, or what service locator applications we tried and which one was the best for us. And actually, when you do the connection, or periodically you would get alerted from the service locator service. For example, a node is out, or it's not replying, or you just took it down, then you don't want to try to connect to it again. So this can be automatic, and this will be the conclusion. This is why I call it as this architecture is an adaptive architecture, because it can adapt to the needs. So, for example, if you have a monitoring service and you realize you have a massive output, or sorry, incoming requests, or the server loads are just getting higher and higher, you can trigger, for example, to create another Amazon image or Rackspace image, deploy the code and just set it in the service locator without any manual steps. And ZeroMQ, so out of the box there are 3 patterns, which I guess most of you are familiar with. And these are request reply for classic client-server communication, remote procedure calls, or path distribution. So it's publish, subscribe, and pipeline fan in, fan out, or actually sync use cases. And when you create I don't know the other examples. Yeah. So for example, you see when you create a socket, you create a socket push and a socket for pooling. So this is where you define these communication pairs. So when you create a socket, so here is the same, ZeroMQ red. So yeah, so that will be the pool version. It's unfortunate I can't scroll down, but yeah, it's actually the same. So when you define the socket, you have to define its role in the communication, and this is one of the ZeroMQ's drawback. You can't change it later. So if a socket was a push socket, then you can't really use it for duplex communication. And I just picked the publisher subscriber use case because it's one of the most popular one, and it's quite useful in microservices, and it has some interesting attributes in ZeroMQ. So subscribers can connect to multiple publishers with pair queuing. So when you do a ZeroMQ connect and you do multiple connection in the same context, it will be a round robin load balancing. So if you write if you run 3 or 4 instances of the same server in the previous examples, then and you just simply multiply or copy and paste the lines, just change the port number, you will see a different response. So if you have add I don't know, the port number to the hello world end, you will see it's literally just do a round robin. And you don't have to do anything for that. So it's a sequential code, but it's not reading like that. That's why it's quite powerful. You don't have to deal with threads. And in some languages, it's quite tricky, like in PHP. So, for example, our previous stack was written in PHP, and doing concurrent stuff is just simply impossible or quite unreliable, I would say. So this was a big help to eat the elephant. If no subscriber connected, publisher drops the messages. So it can be tricky to you have to start your clients first, then your publishers. If you want, when you orchestrate the services, if you don't want to lose any message, you have to start the subscribers first. And as I said, because it's not a synchronized communication. When you connect to a service, if it doesn't exist, it doesn't matter. What matters is when you, for example, send or do a transmission to another service, then that service should exist. If it doesn't exist, then the PubSub use case will drop the message. And if there are multiple clients, but for whatever reason the connection is stalled, then ZeroMQ do queuing in the same process. So it's not something which is in memory or whatever where other processes can connect into, but you don't have to be afraid if there's a, 3-second outage in the network connection, you will lose the messages. And what is quite powerful, filtering happens, sorry, this is wrong. So it happens on the server side. So when you say you want to subscribe to a given channel in the PubSub, so you want to only filter to certain messages, it's filtered on the publisher side, not on the client side. So it's way more efficient than receiving all the messages and you will discard it because it's not for you. Okay, so one trick is what you have to consider when you create such low-level communication in your system is the heartbeat. What happens if you don't transmit anything? In that case, ZeroMQ will drop the connection and it will build up again when you transmit something again. But it might not really So in some cases, you might want to keep alive these sockets. So what's best is, especially if you have multi-part messages, to do a ping pong when you are idle. So if you, for example, transmit a 5 gigabyte of data, then you probably would break down into chunks. And if for whatever reason the one of the side does not recognize a new chunk, then it will send a ping and expects a pong. And if the pong is not coming, then you know this connection is stalled. So this is a good idea. And so ZeroMQ sends messages and not bytes. So if you did TCP communication or UDP in C or C++, you transmit bytes, but ZeroMQ sends messages. So for example, if you send a chunk of message, it stores in the memory, and then it will transmit it in one go. So you don't have to manually, or actually you can't do streaming in ZeroMQ. And ZeroMQ cares only about the transport, so it's a binary transport. And you have to specify the format. It's not SOAP, it's not REST, it's way lower level. So if you want to send a binary, literally the bytes will go there in the same format as you submitted it. And yeah, so you need to define the protocol between these services. So as I said, you transmit actually binaries or in raw mode the data, and if you want to create a kind of language between the client and server, you need to specify the data format. And there are a couple of projects, open source projects, which are available for us and has the one is the Google's invention, or invention idea is the protocol buffers, and it's actually just you have a protocol definition in a text file, and using the protocol buffer tools, it will create you a protocol. So using protocol buffers, you define the protocol in a text file, and both your client and server will or can use it. In this protocol buffer, you can define integers or text or raw bytes, and when you're parsing this message, you can easily understand on both sides, and it's quite fast because it's binary. Another one is the thrift. It's more heavier than protocol buffer. I mean, it's a server stack. Oh, sorry, it's an application because it generates code. It's similar like when you use the visual files for SOAP. If you have the visual file, you can generate the client based on it. And it's quite similar. You described in a text file the protocol. Okay, I would send I don't know first name string 32 characters, last name string 32 characters, and it will generate you both the server and the client code in many languages. But from ZeroMQ perspective, this is out of the top because it won't generate you a ZeroMQ client or ZeroMQ server. But what you can utilize, if you check the source code, you can copy and paste the relevant generated code for the protocol. Does this make sense? Is it? Okay. So, interesting ZeroMQ use cases. You can, for example, use two loggers now, which can listen to ZeroMQ, and you can directly communicate with these loggers with ZeroMQ. So normally you would push it using the syslog commands, or just push it into via TCP to an rsyslog or syslog-ng servers. But using ZeroMQ, it's more easy to configure whether the logger server is on localhost or remote or whatever. Another one, which is one of my favorite, is a Cucumber plugin. You can Cucumber is a behavior-driven testing, behavior-driven design testing tool. So you can, in Gherkin language, you can write your test scenarios and run Cucumber, and it will test your application. And you can write or you can test your contracts or your protocols via this plugin. So you need to install this gem. It's written in Ruby, and it's pretty good, because otherwise how would you in other languages in other use cases it's pretty tough to verify or do functional testing on binary protocols. And there are two web servers. One is written in Ruby, another one is Engine's famous HTTP server, and both has now ZeroMQ plugins or transports. The benefit is engines can alert your application, not, for example, invoking via a CGI instance like in PHP, running PHP FPM. So, but directly communicate to your service, not via TCP, but via ZeroMQ. So if it's in the same host, this connection will be faster. You probably spare some milliseconds of communication, which might matter. And some limitations. As I said, there's no stream-oriented request reply, and you can't reverse the request reply rules. So you can't say, okay, now I'm the server, you are the client, and later they will change. And you can't manage the sockets manually, and you can't do multiplexing. And okay, now we have microservices. Now we can communicate with them in an efficient way. And how can we make this system adaptive? And this is where what we talked some minutes ago. There are a couple of tools what you can use for configuration. These two tools, Puppet and Chef, they are quite popular to use them as a configuration management tool. Puppet, both can have a master slave or a master agent setup, where, for example, you have a Puppet master and all your nodes have an agent, and agents reach either from the catalog the service configuration for your web server, for this and that. You can specify, okay, this node has the role of, I don't know, this is a web server, this is a Logstash server. But the problem is, because these catalogs are pulled periodically, like every 5 minutes, every 10 minutes, and applying these configurations sometimes takes a minute. So it's not really efficient to use to orchestrate or use them as a service locator tool. Another one which is very well known, is originally developed by Yahoo for the Hadoop project, is the Apache Zookeeper, and it's written in Java. It's quite heavyweight. It's robust. It's consistent. It has a strong consistency. That means if you have multiple zookeepers, the configuration. So if, for example, one application changes the configuration setup, let's say, okay, I'm shutting down, so I want to remove myself from the I don't know, mail server pool or mail service pool, all the Zookeeper will be in sync. But this solution is quite heavy. I mean, it's literally 100 and 200 or 300 megabytes in the memory. If budget matters to you, and for most of us it matters, you probably have to buy a higher level instance or rent a higher level instance from Amazon just to use this. It's not really cheap. Another one this is a new project called etcd. It's also written in Google Go. It has one binary, and it's using the REST algorithm for consensus. So, for example, when you use database servers, they try to determine who's the master and who's the master in the communication, and this called consensus or quorum. And there are popular algorithms for this. One is the Plexus, and it's very used, but it's quite heavy, and it takes time to get this consensus from the server. So if you, for example, use MongoDB, it might take half a second to determine who is the master now. If you have a cluster, this is maybe not something you want. And Raft is a bit. It's a different approach. It's way simpler and it's easier to implement. The problem with Plexus, almost every application has a different idea how it should be implemented. And and it's open source. It's written by the Vagrant team. So if you do development, you're probably familiar with the solution called Vagrant. It helps you to have the same environment for everyone, and probably you will have the same setup in your laptop or in your dev environment as the server. Okay, another one is the code console. It's also open source, written in the same language, uses the same REST consensus algorithm. When you use console, you can run it in an agent or in a server mode. When servers are strongly consistent, but agents are not. But they use a protocol called Whisper. And if you have hundreds of nodes, so if you have a massive scale, maybe global hundreds of servers, you can't really do strong consistency because it's just not really feasible. So then the gossip protocol, what it does is always consistent with the nearest neighborhoods. So if you are on the same network, it will shout to all the agents something has changed, and they will spread this to the other agents. And maybe there's a console server in every network, so it will eventually consistent within sub-seconds, but it's way faster than etcd. All these setup or what we use these to expose their settings in environments, the environmental variables, so your application can query the changes or the actual state of the configuration. And it's not; these are not a replacement for Puppet and Chef. These are just for service location and orchestration. And here's the end. Any questions? That's all clear.
I think you touched briefly on some of the drawbacks of microservices,
yeah,
and specifically talking about that you need extensive tooling.
Yes.
One of the biggest challenges we found in my work is kind of managing the deployment process. It sounds really great. I mean, we're trying to sort of get there. We have this idea of how good it will be once we can deploy everything separately, but everything gets tested at the same time. Everything gets integrated together, but then you've also maybe got to run it on your local machine and all this sort of thing. What sort of challenges and tools more specifically are there for that process?
What we use is Docker. It's a virtualization technology written for Linux, so it runs Linux only. And if you have Mac, then there's a tool for that called boot Docker, and you can boot up a very thin layer of Linux, and you can run many Docker in it. The benefit of you don't have to separate the memory or allocate CPUs to the virtualization. So all the process will see all the CPUs and all the memory. So it's not as strong. So if it's a concern for you, you can use SAN or other VMware or whatever you prefer. But we use Docker. Docker has a plugin for Vagrant. So for example, if you want to do a test or you want to simulate your infrastructure in your dev environment, this is a very lightweight solution for that. So you do a Vagrant app, it will boot your infrastructure, it will start the containers, so they will see, or they will appear as an individual node within your VMware or whatever, and that's all. So this is one of the tools what we use. We use Puppet for configuration. So if we want to provision a new change, then we just use it, and we use Console for communication for service location, and Jenkins for continuous integration, Capistrano for deployment. So, for example, if there's a Git commit, the Jenkins will pick up it via a Git post commit hook, and it will do a build and deployment. And yeah.
Yeah, just to follow up. So I'm just wanting to imagine this. So you've got many different microservices.
Yes.
You make changes to one. I imagine it has its own test suite.
Yeah.
But then obviously it could have some effect on some of the other services. So is there like also a kind of...
That's usually a sign of bad design. If you have dependencies on other services, I mean, if you have, for example, have a chain of dependency, then you didn't solve the problem, just you segregated it.
Well, I guess if you were to change the API of the microservice, and something else is
one trick is to version your API. Mm-hmm. So we do an API versioning, for example, on our REST interfaces. So or in ZeroMQ, if you want to add something else, we try to be drawback compatible as possible. But if it's impossible, you can do it in service locator level. So you can say, okay, the version 1 will be deployed on these ports, and version 2 will be deployed to those ports. And if you do a deployment of the client applications or services, then all you need is just to know which version are you compatible with.
Okay, so they're very much plug and play, pluggable into.
Yeah, it's not easy. It's the biggest or the toughest part of the microservices. How do you orchestrate this? And if you have literally thousands of services, it's just something you can't do it manually. So you have to automate it.
Yeah. So and just to clarify, then, I mean, I'm not sure. It is designed in such a way that you really do just have to test the microservices, and then you don't need to test some sort of overarching application or the way they use it.
And it's quite good, because for unit tests you can test the internals of a service, but at the end of the day, what matters is how the whole service operates. And if you want to do a PVT test, a performance and volume test on the whole global system, is maybe it's very expensive. Maybe you will run it a day or two if you want to do a Christmas or Black Friday test, and it's pretty expensive, and it requires a serious effort from the team to create a clone of your actual live environment. But using a small functional test which tests actually the service, it's also perfect if your contracts are well defined. So you do know, because these services are separated or partitioned around a context, and that context can be really well defined. So all the business scenarios, it's way easier than run a whole suite of all the permutation of cases what will happen in the system, and you can still and you will still unable to test the internal or the integrity of the whole system. If you want to apply the chaos monkey practice of Netflix, who if you are not familiar with that, they employ people who just literally plug out cables from data centers or just shut down the electricity, and to test how the system behaves in such critical scenarios. You can't do this or you can't really prepare your system. What will happen if some of the services are not available? If you want to do an end-to-end test.
Thanks.
Okay. Any other question? Okay.
You mentioned before that you need to design the contracts and that you can't leave the
integration to the end. So the whole point is for microservices. So if you do a classic service-oriented architecture, you may have 4 or 5 different components in the system, but here you have hundreds. And if you do heavyweight integration tools, which maybe add, I don't know, 10 or 100 milliseconds each, you will end up 3 seconds of delay, which is unacceptable if you develop games or just classic web application. So that's why I said your contracts has to be well defined, and you have to think about how would you integrate these services. I'm not talking about to expose an API and let system integrators to deal with it. I'm talking about how you as a system architect or software architect has to design these contracts to be as efficient as possible.
But what you usually do, because that sounds a bit like a big upfront design in a way, or what you're saying is that you're based on the services that you have at a particular moment, and then let them go. It's
more about define the protocol, and not really the implementation. So and that protocol should be stable and hard to change. So I don't mean that if you have, for example, a service and you do address, you are based in UK at the moment, but you open up a new office in Frankfurt, for example, and you have to use a different postcode lookup. Your API can't change to reflect to this, but you have to think about it upfront to this. Otherwise, you won't have any benefit of using microservices. Did I answer?
Are there any integration frameworks that can actually plug in? So, for example, we use ActiveMQ and Apache Camel at the minute, and one of the benefits is we can easily wiretap a message, enrich it, transform it, and pass it on to the other service. Is there any way to do that, or is the expectation that you maybe build another microservice to do that transformation, or else basically handle?
Yes, sorry, I forgot to mention ZeroMQ has a special routing mechanism. I forgot to add this, sorry. It's in the previous version, it wasn't there, but now it's there, and it's called proxy. So if you want to, for example, have an intermediate ZeroMQ service, a very tiny one, just to route or redistribute these messages, yes, you can do it, and it's pretty lightweight. And it's way more efficient than connect everything with so if you want to just fan out with a proxy and the same, then yes, you can do that, and I guess it's just 50 lines of code.
Okay.
Okay, if there's no other question, then thank you very much. And sung by a single hit in the Second World War. So it was quite, fortunately you can't see it, but one of the part of the ship had just one single hit, and she was sunk in 3 minutes. And it's the same with big applications. They are too complex to do functional tests in every aspect to realize its flaws and risks. Another one. This is a core graph of a popular open source project written in Java. And the core graph shows us the dependencies between objects, which are marked with white dots, and the classes, which have the other shapes. Some of them are abstract class, some of them are final, and some of them are classic. But the point is, can we determine or describe the behavior of, for example, this instance? Probably we can't, and it's really hard to write behavior-driven tests or behavior test for such software. Okay. Another, maybe a good example for monolithic architecture is the Linux kernel. These numbers demonstrate the changes in the recent 120 days in the life of the Linux kernel. It shows how many developers worked on it, when it was released, how many lines were added, and how much was removed. And these are massive numbers. And even if 2,500 developers contributed to the Linux kernel, only 400 made a significant change on it. That means on the planet, there's only 400 people, probably maybe 500, who can actually understand the whole architecture of such massive project. And it's fine for an open source project because you can enjoy the attention of the developers of the world. But if you work for a client or you develop a platform and you do something very complex, it inherits a huge business risk. So, as a summary, what's wrong with the monolithic architecture? Monolithic architecture intimidates developers. It's hard to do changes in these softwares. It's often they have a complex build script. Good morning, everyone. My name is János, and today I will talk about how we created an adaptive platform at Internet. Who am I? I have a long relationship with software engineering. I started when I was 11 on a Commodore Plus/4, and after the Commodore Basic, I moved to assembly, and I kept as close as possible to the hardware for a long time, and then I moved to the web services when I was at uni, and since then I'm still at the web world. I started a consultancy firm 10 years back, and after 10 years I moved to a consultancy firm called ZeroMQ, and it's one of the largest consultancy firms on the world. I work on projects like Royal Mail, Post Office, Parcelforce.com, Bristol City Council as a software engineer lead. And 5 months ago, I joined to a startup called InternetNew, which is a platform for employers to find fresh talents for their businesses in an automated fashion. We try to capture as many data as possible about the candidates, and we use a matching algorithm, or actually not one, but many, to match internships against the candidates. So we try to minimize the time for the recruitment. And to do this, every startup normally starts with an MVP, or starts with a great business idea, and then they move or they exploit their business ideas, and they reach a point when they need to scale. And this is when I arrived to the project, and from a monolithic architecture we moved to something service-oriented, or actually microservice-oriented architecture. Okay, so I mentioned, and the title of this talk is how to create an adaptive architecture with ZeroMQ. And for first, we should clarify what is an adaptive architecture. And according to the Wikipedia, adaptive architecture is a system which changes its structure, behavior, resource according to the demand. That means normally non-functional requirements has to, or actually the system has to adapt to the new functional requirements, or if the parameters of the external environment changes, then the system should adapt to satisfy those requirements. And as I said, almost every software starts in small as a monolithic platform or architecture. And some examples, I guess you recognize where this photo was taken. It's the Stonehenge, and one of the key thing with Stonehenge is it seems like a successful project, but no one knows anymore what was the original purpose. It's an old project. We can consider it successful because nobody really complained in the last 1,000 years about its functionality. But the original engineers left the project. There's no documentation. There's no tests to understand how the internals of the system work, really. And therefore, if somebody would like to update or upgrade or add some extra functionality to such a system, the new developers would be scared because they don't know where to break these systems. So this is a kind of attributes of a legacy system. So I really like this photo. I don't know how much do you see, but I recognize almost every role as you can utilize in a software projects, like always doer, project manager who is always happy in the background, someone who tries to analyze the state of the system, some senior people who WTFing, and a scared developer who realized what he's facing. Another example is it's a quite tragic example, but it also occurs a lot with big systems. this is the biggest battle cruiser what Britain ever made. Its name is HMS Hood, and when she was laid, and sailors has a bit of dirty mouth, but when she was laid, she immediately became the flagship of the Atlantic Fleet for lightweight. So you shouldn't really copy all of them in the same ratio onto the same server. Some of them maybe it would be enough 5 instances. Some of them has to be deployed to all the servers to have efficient load balancing. Okay, this is a quote from one of the core members of the ZeroMQ team, and he says that the future of code we are told to code. The future code is distributed code. The future code is chatty code. This means there's a tendency to move toward applications or services which heavily talk to each other. If you imagine, for example, if you want to log everything which happens in the system, that's a massive volume of messaging. If you want to also do some or add some flexibility in the system to alter some messages to something else, it's maybe doubles or triples this volume. And then we reach to the microservice. It's actually what is a microservice? It was a kind of movement to distinguish the current state of service-oriented architecture and the lean version of this. Service-oriented architecture started from the paradigm to break down the application into individual parts, individual deploymentable parts, or segregation on the operating system level. So classically, this means you have different runtimes running in the system, and these runtimes communicate with each other. So according to Martin Fowler, services are out-of-process components of the system. And microservice try to do this in a right way. Because in the recent years, if you bought a book about service-oriented architecture, it was more about business, governance, kind of not necessarily technically related stuff. And the whole point is to support not just the business needs, but also the technical evolution. And the people who initially worked on or named their products microservice, they try to distinguish their big, heavy services from their product. Are you guys anyway agree with this? Okay, so if you use or if you try to ever integrate with big massive systems like Microsoft Dynamics with Adobe Lifecycle, and it's pretty tough to deploy them. So if you have a massive software which probably is some hundreds of megabytes or gigabytes, it's pretty hard to do continuous integration on such on such a system. It also, and this is the toughest part. It requires a long-term commitment from technology. If you pick a programming language, you have to maintain it over the life of the whole project. If you pick a database, it's really tough to move from one database to another because all the components has to reflect to the new one. And because of that, you can't really do sufficient or enough functional testing. And if you do functional testing, because a system is very slow moving, it's really hard to, or maybe you can't solve it because there's no enough time to run all the tests between the releases. So if you have to, for example, model a user journey, with payments and all the gateways, and this is a website, then it probably takes a couple of minutes just to create a user, tear down the user, and go through the journey, play all the scenarios. So if you want to do a couple of releases a day, as Netflix or Facebook does, you can't do this with this kind of architecture style. And because these applications are massive, if you develop in Scala or Java, if you occasionally some services need a minute or half a minute to restart, and it's really tough to orchestrate services or do load balancing, because if you have hundreds of servers, you just to go through all the restarts after the successful deployment, this just takes too much time. And for developers, it's also a big problem. It overloads the IDE. If you import the whole project because you want to see all the classes and instances, when you type in the integrated development environment, it offers you auto-completion, and if you have tens of thousands of classes, then it's just makes the whole system slow. Also scales inefficiently. So if you want to deploy and scale horizontally these applications, you have to deploy all these massive chunks onto each server. And some parts probably are more heavy, some of them are more